So we found the distances from the center of mass to our respective masses, namely this and this. Now we also want to find the relationship between the new angular frequencies. Now in general, we have that the angular frequency is equal to the spring constant, the square root of the spring constant, divided by the mass that is on the spring or the mass that is oscillating. So what we want to do is figure out the different k's. Now initially, when it was stationary, it had some total k. But now, since we say that the center of mass is the place that is not moving, we want to consider it as if we're splitting our spring in half to have two springs that are in series with K1 and K2, and these are springs in series. Now, if they're springs in series, that means the force will be the same. Namely, F1 will be equal to F2 will be equal to F. And so we find that if we let x1, x2, and x be the displacement for k1, k2, and k respectively, we find that F is just equal to k times x, or k1 times x1, or k2 times x2. Now, for the case of this, we find that our displacement is just going to be L. So we have that K times L is going to be our displacement. While for K1, we'll call this will be large M and this will be small m. So then from large M to K1 to the center of mass, this will be K1. So we have that K1 times X1 is just going to be this times small m times L over large M plus small m. And this is equivalent to K2 times this, or large M times L. Oops, this would be large M times L over large M plus small m. And so now we can easily solve for the relationship between K1 and K and K2 and K. So we can cancel out the L's on all sides to get that K1 is equal to M plus large M over small m times K, and that K2 is equal to large M plus small m over large M times